Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss why we control distillation column pressure and what are the options for optimizing tower operating pressure. Why are distillation towers designed with controls that fix the tower pressure? Naturally, we do not want to overpressure the tower and pop open the safety relief valve. Alternatively, if the tower pressure gets too low, we could not condense the reflux. Then the liquid level in the reflux drum would fall and the reflux pump would lose suction and cavitate. However, assuming that we have plenty of condensing capacity and are operating well below the relief valve set pressure, why do we attempt to fix the tower pressure? Further, how do we know what pressure target to select? Let us have a look on this pentane-hexane splitter. The tower simply could not make a decent split, regardless of the feed or reflux rate selected. The tower top pressure was swinging between 12 and 20 psig. The flooded condenser pressure control valve, shown in picture, is operating between 5 and 15% open, and hence it is responding in a non-linear fashion. Most control valves work properly only at 20 to 75% open. The problem may be explained as follows. The liquid on the tray deck was at its bubble, or boiling, point. A sudden decrease in the tower pressure caused the liquid to boil violently. The resulting surge in vapor flow promoted jet entrainment, or flooding. Alternately, the vapor flowing between trays is at its dew point. A sudden increase in tower pressure can cause a rapid condensation of this vapor and a loss in vapor velocity through the tray deck holes. The resulting loss in vapor flow can cause the tray decks to dump. Either way, erratic tower pressure results in alternating flooding and dumping, and therefore have reduced tray efficiency. While gradual swings in pressure are quite acceptable, no tower can be expected to make a decent split with a rapidly fluctuating pressure. Selecting an optimum tower pressure. The process design engineer selects the tower design operating pressure as follows. 1. Determines the maximum cooling water or ambient air temperature that is typically expected on a hot summer day in the locale where the plant is to be built. 2. Calculates the condenser outlet, or reflux drum temperature, that would result from the above water or air temperature. 3. Referring to this picture, the designer calculates the pressure in the reflux drum, assuming that the condensed liquid is at its bubble point. Adding 5 or 10 psig to this pressure for pressure loss in the overhead condenser and associated piping, the designer then determines the tower top pressure. Can the unit operator physically deviate from this design pressure? Raising the tower pressure target. A process engineer had a contract in a refinery to revamp a hydrocracker fractionator, which produced naphtha, jet fuel, and diesel. The bottleneck was tray flooding. At higher feed rates, the kerosene would carry over into the overhead naphtha product. The engineer's initial plant inspection showed that the tower top pressure was 24 psig. The relief valve was set at 50 psig. By raising the tower operating pressure to 30 psig, the flooding was stopped, and his contract was cancelled. Why? Ambient pressure at that refinery was about 13 psia, or pounds per square inches absolute versus 14.7 psia at sea level. Higher pressures reduce the volumetric flow of vapor. In other words, volume is inversely proportional to pressure. The pressure we are concerned with is the absolute pressure. Initial pressure equals 24 psig plus 13 psi equals 37 psia. Final pressure equals 30 psig plus 13 psi equals 43 psia. The absolute tower pressure, in psia, increased by 17%, and hence the volume as well as the velocity of vapor through the valve tray caps declined by 17%. The reduced vapor velocity reduced the dry tray pressure drop, thus reducing both the spray height above the tray deck and the liquid backup in the downcomers. Another reason to raise tower pressure is to permit higher reflux rates. If the pressure controller in picture is set too low, then during hot weather, when condenser capacity becomes marginal, the level in the reflux drum will be lost. If we then raise the pressure set point, the drum will refill. But why? Raising the tower pressure also increases the reflux drum pressure, raising, in turn, the temperature at which the vapors condense. The rate of condensation is then calculated from the following. Q equals U times A, Tc Ta, where Q equals rate of condensation in BTU per hour, A equals heat exchanger surface area in feet square, U equals heat transfer coefficient in BTU per hour square feet degree F, Tc equals condensation temperature of vapors in degree F, Ta equals temperature of air or cooling water in degree F. Raising the tower pressure increases Tc. Lowering the tower pressure. In general, distillation columns should be operated at a low pressure. For example, picture shows an isobutane normal butane stripper. This fractionator is performing poorly. A computer simulation of the column has been built. The column has 50 actual trays. However, in order to force the computer model to match existing operating parameters like reflux rate, product compositions, 10 theoretical separation stages, that is 10 trays, each 100% efficient, must be used in the model. This means that the trays are developing an actual tray efficiency of only 20%. A field measurement indicated a pressure drop of 2.0 psi. Assuming a specific gravity of 0.50, then the pressure drop per tray in inches of liquid is 2.0 psi tower increment P divided by 50 tray times 28 inch H2O divided by 1 psi times 1.0, specific gravity of water, divided by 0.50, specific gravity of butane, equals 2.24 inch liquid increment P per tray. As the wear height of the trays is 3 inches, it is a safe assumption that the low tray efficiency is due to tray deck dumping, rather than flooding. As shown in this picture, this column has no reflux. This is a typical design for strippers. When feed is introduced on the top tray, there is no need for reflux. In order to improve tray efficiency, it will be necessary to increase the vapor velocity through the trays, to increase the pressure drop to at least 4 or 5 inch of liquid per tray. If the reboiler duty were simply increased, the concentration of the heavy component, normal butane, and the light overhead product isobutane would escalate exponentially. Another method, however, that does not involve increasing either the reboiler duty or the mass flow of vapor through the trays can be used to increase vapor velocity. By lowering the tower operating pressure, the volume of vapor flow bubbling up through the tray decks may be increased without changing the mass flow. For instance, if the tower pressure were reduced from 105 psig or 120 psia to 45 psig or 60 psia, then the velocity of vapor through the sieve holes on the trays would double. This would lead to a substantial increase in the dry tray pressure drop, and hence reduce tray deck leakage. To lower the tower pressure, the hot vapor bypass pressure recorder controller (PRC) valve is closed. This forces more vapor through the condenser, which, in turn, lowers the temperature in the reflux drum. As the liquid in the reflux drum is at its bubble point, reducing the reflux drum temperature will reduce the reflux drum pressure. As the stripper tower pressure floats on the reflux drum pressure, the pressure in the tower will also decline. The net effect of reducing the stripper pressure was to greatly reduce the amount of isobutane in the heavier normal butane bottoms product. There is no doubt, most of the improvement in fractionation was due to enhanced tray efficiency, which resulted from suppressing tray deck leaking or dumping. However, there was a secondary benefit of reducing tower pressure: increased relative volatility. Relative volatility. The chart shown in this picture is called a Cox, or vapor pressure, chart. It shows the pressure developed by pure component liquids at various temperatures. The interesting aspect of this chart is that the sloped lines, representing the vapor pressures of pure hydrocarbon components, spread apart at lower pressures. This results in an increase in the ratio of the vapor pressures of any two components. The vapor pressure of a light component at a given temperature divided by the vapor pressure of a heavier component at the same temperature is called the relative volatility. You can use a vapor pressure chart for relative volatility calculation. One source is your API data book. For practice, calculate the relative volatility of isobutane and normal pentane at 140 degrees Fahrenheit. Answer will be 4.0. Next, calculate their relative volatility at 110 degrees Fahrenheit. Answer will be 4.9. Note that the relative volatility has increased by about 20% at the lower temperature and pressure. This increase in relative volatility allows one to make a better split at a given reflux rate, or to make the same split at a lower reflux rate. We can quantify this last statement as follows. RVL, RVH, divided by RVH1 equals DRF. Where RVH equals relative volatility at a high pressure, RVL equals relative volatility at a low pressure. DRF equals percent reduction in the reflux rate when the same degree of fractionation is desired. Reducing reflux saves reboiler duty. In addition, the lower pressure will reduce the tower bottom temperature, and this also cuts the reboiler energy requirement. For most distillation towers, the energy cost of the reboiler duty is the main component of the total operating cost to run the tower. Incipient flood point. As an operator reduces the tower pressure, three effects occur simultaneously. Relative volatility increases. Tray deck leakage decreases. Entrainment, or spray height, increases. The first two factors help make fractionation better, the last factor makes fractionation worse. How can an operator select the optimum tower pressure to maximize the benefits of enhanced relative volatility and reduce tray deck dumping without unduly promoting jet flooding due to entrainment? To answer this fundamental question, we should realize that reducing the tower pressure would also reduce both the tower top temperature and the tower bottom temperature. Therefore, the change in these temperatures, by themselves, is not particularly informative. But if we look at the difference between the bottom and top temperatures, this difference is an excellent indication of fractionation efficiency. The bigger this temperature difference, the better the split. For instance, if the tower top and tower bottom temperatures are the same for a 25 tray tower, what is the average tray efficiency? Answer is 100% divided by 25 is equal to 4%. The basis for the 100% is that if the tower top and bottom temperatures are identical, plus or minus a few degrees, then the entire tower is functioning as if it represented a single perfect theoretical fractionation stage. The fractionation efficiency of a theoretical stage is equal to one perfect tray operating at 100% efficiency. This picture illustrates this relationship. Point A is the incipient flood point. In this case, the incipient flood point is defined as the operating pressure that maximizes the temperature difference across the tower at a particular reflux rate. How, then, do we select the optimum tower pressure to obtain the best efficiency point for the trays? Answer is, look at the temperature profile across the column. The phase rule in distillation. This is perhaps an idea you remember from high school, but never quite understood. The phase rule corresponds to determining how many independent variables we can fix in a process before all the other variables become dependent variables. In a reflux drum, we can fix the temperature and composition of the liquid in the drum. The temperature and composition are called independent variables. The pressure in the drum could now be calculated from the chart in picture. The pressure is a dependent variable. The phase rule for the reflux drum system states that we can select any two variables arbitrarily, temperature, pressure, or composition, but then the remaining variable is fixed. A simple distillation tower, like that shown in picture, also must obey its own phase rule. Here, because the distillation tower is a more complex system than the reflux drum, there are three independent variables that must be specified. The operator can choose from a large number of variables, but must select no more than three from the following list. Tower pressure, reflux rate or reflux ratio, reboiler duty. Tower top temperature. Tower bottom temperature. Overhead product rate. Bottoms product rate. Overhead product composition. Bottoms product composition. The prior discussion assumes that the feed rate, feed composition, and heat content of the feed, that is enthalpy, are fixed. My purpose in presenting this review of the phase rule is to encourage the routine manipulation of tower operating pressures in the same sense, and with the same objectives, as adjusting reflux rates. Operators who arbitrarily run a column at a fixed tower pressure are discarding 1/3 of the flexibility available to them to operate the column in the most efficient fashion. Moreover, this is true regardless of whether the objective is to save energy or improve the product split. That is all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.